In the last two videos, we looked at the various processes that are occurring in real pipe flows that can lead to losses. In this video, we're going to look at how to quantify those losses and work out how much of our total pressure head we're going to lose due to these processes. So let's start with an example. Here I've got a constant head tank that has a water level of 209 millimeters. The system has a pipe that's 1.25 meters long and a valve on the end of that pipe. And we have three pressure tappings along the pipe, one just after the tank, one 0.5 meters further down the pipe, and another a further 0.5 meters along the pipe. So we can measure the system's pressure head in the supply tank and at 3 points along the pipe. I've set a flow in this system by opening the valve at the end of the pipe about half open. We can get the velocity in the pipe by measuring the discharge and using the volumetric method described in lesson 1 part 1. When measuring the discharge, I collected 0.65 litres of water in 5 seconds, which gives a discharge of 0.13 litres per second, and in my pipe with a diameter of 15 millimeters, this corresponds to a mean velocity of 0.736 meters per second. Here's my working out if you want to pause to see how I've done this process. We know that we're going to lose energy in this system due to friction, viscosity and turbulence. So can we measure how much energy we've lost along this pipe? Let's define 4 points along this system and work out the total pressure head at each point. Point number 1 is the water surface of the tank that's feeding the pipe. Point number 2 is in the pipe just after the pipe has left the tank. Point number 3 is 0.5 meters further down the pipe than point number 2. And point number 4 is 0.5 meters further down the pipe than point number 3. So in total we have 4 points where we can measure the total pressure head in the system. So let's start with point number 1, the water surface of the supply tank. If we write out Bernoulli's equation at point number 1, we can work out the total pressure head at this point in the system, which we know is the sum of the elevation terms, at the pressure terms, at the velocity terms. If we think back to the process we looked at in lesson 2, we know we can assume the pressure is 0 at the water surface of the tank, because there's no body of water pushing down on this point in the system, and we're assuming atmospheric pressure is 0. We can also assume the velocity terms at the water surface of the tank are 0, because the velocity of the water surface is going to be negligible compared to the velocity of water in the pipe. So we can cancel out the pressure head and the velocity head, which means that all of our energy at the water surface of the tank is in the form of potential energy in elevation. And we can see by looking at the gauge on the side of the tank that the elevation of the water surface is 209 millimeters or 0.209 meters. So the total pressure head at point 1 is 0.209 meters. So in the tank we have a total pressure head of 0.209 meters. Let's imagine how this energy level will change as we move throughout the system. Let's draw a line to show the level of total pressure head at all points in the system. In the tank, the total pressure head is a constant value of 0.209, so we'd have a flat line at this point in the system. If we had no loss of energy at any point in the system, then we'd have this same level of energy at all points throughout the pipe, so this line would remain constant. Pressure head may convert between elevation, pressure and velocity, but the total pressure head at any point in the system would be 0.209 meters. But as this is a system in the real world and we're going to get friction, viscosity and turbulence in this pipe, we're going to lose energy as we move down the pipe, and we can see how much we're losing by doing the same calculation we've just done at points 2, 3 and 4. So let's do this calculation at point 2. Again, we can write out Bernoulli's equation. At point number 2, we haven't got any elevation because the pipe is at the base of the system, but we do have pressure in the pipe and we do have velocity in the pipe. We've already worked out the velocity in this system using the volumetric method, which is 0.736 meters per second, and we can simply read the pressure head at this point in the pipe off the gauge at point 2, which is 125 millimeters or 0.125 meters. So the total pressure head at point number 2 is going to be 0.153 meters. So we can see we've had a sudden loss of energy as the pipe exits the tank. In the tank, the total pressure head is 0.209 meters, and in the pipe just after the tank, the total pressure head is 0.153 meters. So we've had a loss of total pressure head of 0.056 meters as the pipe leaves the tank, and this is a sudden loss of total pressure head. We call this a local loss of energy. A local loss is where we get a sudden drop in energy at a single point in the system. So for example, when water goes round a bend, we get a sudden loss in energy as it takes some energy for the water to orientate itself around the bend. Or, as we're looking at in this example, when water leaves the tank and goes into a pipe, we get a loss in energy as the water is losing energy while it's forcing itself into the new geometry. So as we go from the tank to the pipe, we get this sudden drop in energy and we're losing 0.056 meters of total pressure head. On our total energy line, this would show us a sudden drop in energy at the location in the system where we've had the local loss. Let's have a go at doing the same calculation at point number 3, which is halfway down the pipe. We can write out Bernoulli's equation at point number 3, and at this point, like point number 2, we have no elevation because the pipe is at the base of the system, but we do have pressure and velocity. We already know the velocity, which is 0.736 meters per second, and we can read the pressure off the gauge, which is 91 millimeters or 0.091 meters. So if we plug those numbers into Bernoulli's equation, we get a total pressure head at point number 3 of 0.119 meters. Again, we can see that we've had a drop in total pressure head between point number 3 and point number 2. Between point number 3 and point number 2, we've lost 0.034 meters of total pressure head. This loss isn't because of any particular fixture in the pipe. This is what we call a continuous loss due to friction and turbulence. So as the fluid moves down the pipe and experiences friction as it moves down the pipe and resistance from turbulence, you'll have a continuous loss of energy, and the further the fluid travels down the pipe, the more energy the fluid is going to lose. So between point number 2 and point number 3, we've lost 0.034 meters of total pressure head, but this wouldn't be a sudden drop in energy. this would be a continuous loss that would draw with a line with a gradient. The loss is continuous because it's due to friction and turbulence in the pipe. So the further we travel down the pipe, the more energy we're going to lose. Finally, if we do the same calculation at point number 4, we end up with a fairly similar result to what we found at point number 3. We can write out Bernoulli's equation, and again the elevation term will be 0 because we're at the base of the system. The velocity is the same as all points in the system, so is 0.736 meters per second. We can read the pressure off the gauge, which is 0.049 meters. And this gives us a total pressure head at point number 4 of 0.077 meters. So what we can see is that as we've travelled further down this pipe, we've lost even more energy due to friction and turbulence. So over the meter that the water has had to flow down the pipe, we've lost in total 0.076 meters of energy due to continuous losses in the pipe. It's important to understand the difference between local losses and continuous losses. Local losses are losses that occur at one particular location in the pipe, whereas continuous losses will continue however far down the pipe we travel. So as our pipe exits the tank, we've lost 0.056 meters of energy due to losses as the water has forced its way into the main pipe. But this loss would be the same regardless of how long the pipe was. This particular loss would just be one single loss at this location of 0.056 meters. Whereas the continuous losses due to friction and turbulence would continue to get larger the longer we made the pipe. It can be useful to consider the gradient of the continuous losses. Over 1 meter in our pipe, we've had a continuous loss of 0.076 meters. So we could say the gradient of the energy line is 0.076 meters per meter, meaning that for every meter of pipe we have, we'll lose another 0.076 meters of energy. In the system that we're looking at the moment, the energy that we've lost due to local losses is fairly similar to the energy we've lost from friction and turbulence. However, if the pipe was 100 meters long, then the losses due to friction and turbulence would be massive compared to the local loss, and we could probably neglect the local loss from our calculation. So far in this video, we've looked at losses of energy in the system due to local losses and due to continuous losses. And we've been able to do this because we've installed 3 pressure gauges along this pipe. But we can't always measure the pressure in a pipe, and more often than not we need to be able to predict what losses we're going to get as a result of local losses and continuous losses. So let's have a go to see if we can use some theory to predict how much energy we're going to lose in this system. We can predict local losses with the following equation, where our local losses are equal to a local loss coefficient K times U squared over 2G. So our total loss in pressure head for a local loss is equal to the local loss coefficient times the velocity head of the system. Each fixture in a system will have its own local loss coefficient K, and these can normally be looked up in a textbook. For my system, the tank connector that links the pipe to the tank has a local loss coefficient of 2. So if we wanted to predict how much energy we're going to lose between the tank and the pipe, we could use this equation with K equals 2 and the velocity that we've got in our system. So if we plug those numbers into the equation, we can see that we should be expecting to lose 0.055 metres of energy using this equation, which would give us a predicted total pressure head at point 2 of 0.154 metres, which is almost exactly the same as the total pressure head that we measured using the velocity and the pressure. So for any point where we're going to get a local loss in the system, we can use the local loss equation as long as we know the loss coefficient K. To work out continuous losses due to friction and turbulence, we need to use something called the Darcy-Weisbach equation. This equation tells us how much energy we're going to lose as a result of continuous losses. In this equation, F is something called the friction factor, which quantifies losses due to friction and turbulence. L is the pipe's length, D is the pipe's diameter, and U squared over 2G is the velocity head in the system. So for our system, we know the velocity, we know the length, and we know the diameter. But the one thing we don't know is what this friction factor is. This factor that's going to quantify how much energy we've lost due to friction and turbulence. To work out this parameter, we're going to need to use something called the Moody Diagram, which we'll work through quickly now, but I've put the link to a more comprehensive explanation of how to use this chart into the description. So this is a Moody diagram, and this diagram will allow us to find the friction factor of a flow based on the flow's Reynolds number and the roughness of the pipe. So the first thing we need to do is work out the Reynolds number. Reynolds number is important because the amount and type of turbulence we have in the pipe is going to affect our total head loss. Reynolds number is the mean velocity of the flow times by the pipe's diameter divided by the kinematic viscosity. Our flow has a mean velocity of 0.736 metres per second, a diameter of 0.015 metres, and we can assume the kinematic viscosity as 1 times 10 to the minus 6 metres squared per second. If we enter these numbers into the Reynolds number calculation, we get a Reynolds number of 11040. We can round this to 11,000. So the first step is to find the Reynolds number on the x-axis, which is 11,000 for our flow, and draw a vertical line straight up from the Reynolds number. We can now see that our Reynolds number line is crossing a load of these blue lines, and each one of these blue lines represents a different pipe with a different pipe roughness. So what we need to do is find out which one of these blue lines corresponds to our pipe. Each of the lines is given a different relative roughness, and the definition of relative roughness is the roughness of the pipe in millimetres divided by the pipe diameter. We can look up the roughness of our pipe in the table in the bottom left of this chart. Our pipe is perspex, so it has a roughness of 0.0025 millimeters. So if we divide the roughness by the pipe diameter in millimeters, this gives us a relative roughness of 0.00016. We can round this value to 2 times 10 to the minus 4, and we can see that we have a line that corresponds to this relative roughness. So let's highlight the line that corresponds to the relative roughness of our pipe. We're now just looking for the point where our Reynolds number line crosses our pipe's roughness line, and at this point where the two lines cross, we're going to draw one final horizontal line that intercepts the y-axis, and this will give us our friction factor. Here we can see the friction factor is 0.03. So now we've got the friction factor from the Moody diagram. We have all the terms we need to calculate the loss of energy due to friction and turbulence between point number 2 and point number 3. Our friction factor is 0.03. We've just got this from the Moody diagram. We're calculating losses over 0.5 metres of pipe length, so this will be our length. The pipe diameter is 0.015 metres and the system's velocity is 0.736 metres per second. This gives us a total loss due to friction and viscosity of 0.028 metres. If we minus this from the total pressure head at point 2, we get a predicted total pressure head at point 3 of 0.125 metres, which is a reasonable prediction of the measured total pressure head at point 3. We can do exactly the same procedure to work out how much energy we've lost between point number 3 and point number 4. We can see for the final part of this system, the predicted head loss doesn't quite match the actual head loss as well as it has done for the previous two examples, but it still gives a really good ballpark estimate of how much total pressure head we've lost. When I was looking at the system after the tests, I discovered that despite my best efforts, the final part of the pipe wasn't exactly level, and this leads to a small offset on the pressure gauge, which has caused this inaccuracy in the final result. So in this lesson, we've moved on from our idealised view of this system in lesson number 2, where we were assuming no loss of energy at any point in the system, to a much more realistic picture of what's going on inside this pipe. In part 1 we looked at the effects of friction and viscosity. In part 2 we looked at laminar and turbulent flow. And in this video we've looked at how those processes are going to lead to losses in our pipe and how we can predict what those losses are going to be. In the next lesson we're going to bring all of the theory we've learnt in lesson 2 and 3 together to incorporate our prediction of losses inside Bernoulli's equation.